Hello and welcome to my proof on the equivalence to Euclid's fifth postulate. The substitution that I chose was that through any three non-collinear points there passes a circle, and we're going to prove that in both directions today. The first thing we want to look at is assuming the basis E and Euclid's fifth postulate and showing that that implies that through any three non-collinear points there exists a circle. So I just have a generic three non-collinear points, A, B, and C, and we want to prove the existence of a circle through these 3 points. So with letting those 3 points be non-collinear, I am going to construct A, B, and B, C using postulate 1. I'm then going to let M and N be the perpendicular bisectors of A, B, and B, C, respectively, intersecting at points P and Q, respectively, with A, B, and B, C. So one thing that's not necessarily noted on a lot of these slides, but is true, is my definition of perpendicular bisector. It will come into play in just a little bit, and it is true, but in order to not kind of overdo the annotations on a lot of these until we get to the point that we need it, they're not going to be on there. So keep those in mind. We'll come back to them in a second. What I want to do now is I want to extend segment AB to line AB using postulate 2 and letting the intersection of lines N and AB be the point R. And that point's actually pretty important if we look at different cases of non-collinear points, which I'll talk about a few of those once we get there. What we're going to do now is we're going to let K be the perpendicular to AB at point R. So it's not noted on here. I forced the program to show that angles 1 and 2 weren't right angles for no real reason. They are right angles, and we're going to use that in just a second. But I have labeled some angles here that we're going to reference. What this actually tells us is that by proposition 28, since angles 1 and 2 are, since they are right angles, they do add up to 2 right angles, that lines K and M are parallel. And then one thing to note is that angle 3 is less than angle 1 by common notion number 5, just that the sum is greater than its parts. And so we need that in order to show that I have angles 2 and 3, which add up to less than 2 right angles. And by Euclid's fifth postulate, since angles 2 and 3 add up to less than 2 right angles, then lines N and M will intersect at point O, which has to be to the right of line AB, and that point O is later going to turn out to be the center of our circle. And now we're going to actually look at those triangles that are formed with point O. I've drawn 3 segments of coming from point O: OA, OB, and OC. So to my 3 non-collinear points, and we're actually looking at all the different triangles formed, the 4 different triangles that are formed, and we're going to prove some things about those triangles. So since the red lines OP and OQ were perpendicular bisectors, I know that they intersect at right angles. So here I have forced those angles to be right, or just the notation that those angles are right, and that since they're perpendicular bisectors, AP is congruent to BP and BQ is congruent to CQ. That's important because that gives us enough information with the shared sides between triangle OPA and OPB, as well as between OQB and OQC, the shared sides of those perpendicular bisectors, the OP and OQ, I can note those as well for the time being. I'm going to take over that notation in just a second. But those shared sides let me use proposition 4 to say that those four triangles are pairwise congruent. So OPA is congruent to OPB, and OQB is congruent to OQC. Using that, like I said, I took over the three-line notation, not saying that either of these perpendicular bisectors are congruent to these lines OA, OB, or OC. But I've shown it in the picture as one step. It's realistically two steps, that OA is congruent to OB and OB is congruent to OC by proposition 4, the corresponding parts of those congruent triangles being congruent. And then by common notion 1, we actually get that those three segments are congruent. So by the definition of a circle with those three segments congruent, I now have a circle that's centered at point O with a radius of OA, or OB, or OC. That selection isn't important at all, as they're all congruent. So there we have a circle through those points with the center at the intersection of the perpendicular bisectors. It should also be stated that in what we've been talking about, I had, if we look back, I had angle ABC as an obtuse angle. That's not an important selection. We can see here that if ABC is acute, the only thing that really changes is kind of the direction of line N and where that forces my intersection of line N and line AB. That point R that we talked about used to be up above point B, as point C was above point B in this picture. So point R has just moved down below. The center of the circle is still at the intersection of these perpendicular bisectors, and all the same aspects of the proof apply. Just some minor details that have been that get switched around. If I had angle ABC as a right angle, I don't know why it didn't snap to a right angle, but if I had a right angle here, the only thing that I would do is shift my focus from the perpendicular bisectors that I chose, being AB and BC, to looking at the perpendicular bisectors of AB and AC, and they still intersect. Using Euclid's fifth postulate, they still intersect, and I still get the same congruent segments from OA to OB to OC. So those, all I end up doing in the right angle case is I avoid the perpendicular bisector of BC, and I focus on the perpendicular bisector of AC. So I avoid this one here, and I shift my focus to the perpendicular bisector of AC, and I follow the acute case. So with half of this proved, we're going to now shift our focus and assume the basis E and assume our substitute that through any three non-collinear points there exists a circle, and we're going to prove Euclid's fifth postulate using that. So we're going to start with line M and point D that's not on line M. We're then going to use proposition 12 to construct line DE that's perpendicular to M through point D. So I've just given myself a perpendicular line. I'm going to select point B just in a way that it's between point D and point E. As the selection of point D was completely random, you might ask, well, what if B was above point D? Then I would say to select a new point D and proceed from there. So with that selection of B, I am going to essentially reflect point B across line M And the way I'm going to do that is just to say to consider point A on line DE, excuse me, on line DE such that BE is equal to AE in a way that A is not equal to B. So the only way for that to be the case is for it to be on the opposite side of line M, and I have two congruent segments here with still a right angle at point E between line DE and line M. Next, I'm going to use proposition 11 to let line N be a perpendicular, to be the perpendicular to DE that goes through point D. So I've given that line N, and now I'm going to construct segment DF with point F in a way that forces this angle 3, and I didn't want to type out all the angles, so that forces angle 3 to be less than angle 1. I know that angle 1 here is actually a right angle, as it's the intersection of two perpendicular lines. But I'm selecting point F such that angle 3 is less than a right angle. If I were to, the only real case to avoid is where point F is on line N, and I'll talk about that in a second. But if point F is above, or angle 3 is greater than angle 1, we would simply shift our focus to the other side of this line as the only stipulation that we have. So I guess you could say without loss of generality, select point F to where it is, to where angle 3 is less than angle 1. The next thing I want to do is to project point B to line DF, and there's no stipulation that this point G, where my new line is going to intersect line DF, my BG line is going to intersect DF. There's no stipulation that point G is between D and F. It can be outside of it. There's no problem there. Just in this representation, it's in between. And then I'm going to use that to, again, in a way, reflect point B across this line DF, making sure that my new point C that I'm constructing here is on line BG, and BG is congruent to CG. Again, in a way similar to how we constructed point A from point B, but similarly, I don't want B and C to be the same point, so it has to be on the other side of the line. That gives me 3 points that are non-collinear. So looking back, if point F was on line N, the issue there is that point C would then be on line DE, along with points A and B, and I would not have 3 non-collinear points. So that was the forcing of F being not on line N. That was the only real stipulation, and I just went with, without loss of generality, let angle 3 be less than angle 1. So in other words, that gives me points A, B, and C as non-collinear points, and therefore there must be a circle that passes through them. And given that, with lines M and DF, M is this line right here, sorry that it wasn't marked, with lines M and DF being constructed as the perpendicular bisectors of A, B, and BC, they'll intersect at the center of the circle that contains points A, B, and C. So they're going to intersect right here. And that is going to make way for the fact that they're going to intersect at the right of line DE. So they're intersecting to the right of line DE. If we were to suppose that they were to intersect on the other side, then they wouldn't be the center of this circle, as the center of the circle is not going to be outside of the circle. So they're intersecting on the side where the two angles, this right angle and angle 3, were less than two right angles. And that proves Euclid's fifth postulate. Thanks for tuning in, and we will see you later.